Yeah, I heard there's
Sorry,
a
was a very
party
nice.
night. Yeah, yeah, no worries. And again, who knows how long it will actually be. So.
So we're going to start in 5 minutes. If you have any roommates or dear friends that really want to attend, please tell them to hurry up. Just as a show of hands, as a survey, who came home or to your room before midnight? Oh, nice, nice, that's good. That's why you're here. That's first. Who came to your house before? Oh, no, sorry, let's do it in reverse. Let's do it in reverse. Who came home after midnight? So keep your hand up. Who came after 1 a.m.? Okay. After 2 a.m.? Okay. My hand is still up as well, just to let you know. After 3 a.m.? Oh, wow, and it's here. Okay. So I guess some of the people that will arrive later probably is after 4 a.m. Let's hope not. Okay, just a reminder also that all the questions can be submitted on Slido, on Keynote. Now you know the drill, so feel free to post your question even during the talk. We'll have a few minutes at the end to ask questions to Emily. And then we can also take it from here if there is a question in the house. Okay, you ready?
Sure.
Yeah. So, Emily Morehouse Valcarcel.
You got it.
We practiced that. Is a Python software developer, but especially a core developer for Python, and is now steering member for the Python Software Foundation. So it's a lot. It's the perfect conference to be in. today for this last day of the conference. Is going to talk about a very important topic. We touch here and there the importance of exploration, but especially today we're talking about curiosity and how this infuse also the process of work life, and we're very curious about your personal experience on that as well. Okay, so if we are all ready, I'll let you the stage. So a super big applause to Emily.
Hello, everyone, and welcome to your final day of PyCon Italia. I am absolutely thrilled to be here with you all. And especially thank you to all of you for making it here. I know that last night was a late night. Hopefully we didn't have too many spritzes and too much wine and too much fun. I was super bummed. I apparently left right before the concert started last night. But I heard that that was quite a feat to see. So I'm here to present to you my talk today, Stay Curious, Reflections on Passion, Risk-Taking, and Reinvention. So first, a little bit about me. I'm Emily Morehouse-Valcarcel. I am the co-founder and director of engineering, and wow, okay, it is early for all of us. Co-founder and director of engineering of a company called Cuddlesoft. We are a full-cycle digital product development company, so we take people from those sort of like napkin sketch ideas through user experience design, building out their software, maintaining it, scaling it. So we do everything from web, mobile, IoT, and the cloud. I'm also a Python core developer and a Python steering council member. So essentially what that means is Python core developers are the folks who actually develop the Python language itself. There are a lot of people who go into that process, but Python core developers are specifically the ones who just happen to have commit privileges on GitHub, but are sort of like that core group of people that
One quick announcement, please, if you want to ask questions, go on the schedule and ask question on, click the button ask question on the schedule for this talk and ask it to them to the Slido. Thank you very much. And welcome to Alexander Darby at your own call.
Hi everyone. Thank you everybody for coming. Great to see so many of you here. So I'm Alexander. I'm a software engineer working in cybersecurity. I work at Palo Alto Networks in a team called Unit 42 where we look at threat intelligence. And this talk is about how you can attack your own code. And I had the idea for this talk because I work quite a lot with people called penetration testers. If you don't know what that term means, it's the industry term for someone who's an ethical hacker, so somebody who gets paid to attack software systems. And I noticed while hanging out with these people that the way they talk about attacking systems is really different to how I think we as software engineers think about defending systems. So I thought it would be a cool idea to try and learn how people hack things, try and learn how they attack things, and then use that to defend software a bit better. But I had some issues when I first tried to do this. I went on a website called tryhackme.com, and on that website you can learn how to hack things. But I found it really boring. Before I go into this next bit, could you raise a hand if you've ever hacked something? Okay, so a bit under half. I don't know how everyone here found it, but for me, I found it pretty boring. If you're hacking something, you don't really get to write beautiful code. You don't get to write stuff that you're going to maintain for years. You're kind of just looking for a vulnerability. You're looking for a foothold. And quite often, you might just copy and paste someone else's code from a vulnerability database, from something someone else has put together. It might not work perfectly, and you just have to get it to work. And it can be in any language. If I'm hacking, I don't care if it's in Java or C or Python. I just need to get access to the system. So I found that kind of boring and stopped doing that. But what the rest of this talk is about is a way where I think you can learn about hacking things without having to become a hacker. And that is what this next slide is about. So another quick story about some of the people I work with or I'm friends with who are penetration testers. Again, if you don't remember, that's someone who's paid to hack things ethically. If they fail or pass an exam, their salary can go up by 10 or 20% or down by that much. So it's a really big deal that they have to take certifications where they try and hack things all the time. So it's a little bit like being a doctor, I think. You have lots and lots of exams all the time, very regulated profession, because obviously it's a crime to hack things if you don't do it in the right and proper way. As a result, people write tons of blog posts to try and help each other with training. So they write a lot about how they hack things, how it went. And I think this is really useful if you're a software engineer, because it means you don't actually have to spend all that time learning a new skill set about how to attack things. You can just read these blog posts. So I'm going to give two examples here. One is this. This is a Medium page, InfoSec write-ups. And this is a collection of blog posts by hackers who talk through how they attack things there. And then this is a GitHub repo, which contains basically loads of malicious code. And all hackers put stuff there for the kind of payloads that they want to send to us, to the software systems that we build. So a ton of useful information there. And then the next stage of this slide, this kind of 4 stages of hacking is, as I understood from reading lots of these blog posts and trying to understand how people attack things, I felt pretty much everything goes through these 4 stages. So I'm going to explain this a bit with a metaphor. It's a bit like if you're a burglar trying to break into a house. The first stage would be enumeration. So if you're looking at a house, I've never done this, but this would be like, if you're, maybe you call them up to see if they're at home at a particular time or not. You go walk around the house, see if there's a window that gets left open somewhere. In the software world, that's going to be something like, what ports are open on this service? If it's a web app, what are all the endpoints? How can I get a foothold? It might be, what version of the software is it running? This kind of stuff, looking for things that can help equip you to then find the right payload. So if we go back to the burglar example, a payload might be, like say you found a window on the second floor that was open. A payload might be a ladder that you bring one night to climb into the house and get in. If you're a hacker, it's going to be malicious code of the kind that is on that payload's all the things website. And very often, as we'll see later, that means you'd find something that just already exists. It matches a particular tech stack. It's already been hacked, and you just need to get the puzzle piece to fit into the right area. The next stage I'm going to call harvesting credentials. Again, in my metaphor, this would be like, once you've broken into the house, you might be looking for keys. Maybe you want to find a room with a safe that has like a car key or a room to some other door. In the software world, suppose you've got a shell on someone else's server. That's going to be things like API keys, usernames, passwords, SSH keys. And the reason that you want these is typically for the next step, escalating privileges, where you want to break out and basically get more power, do more bad things. My burglar analogy is kind of going to fall apart a little bit here, but I guess it would be like if you then took the car for a ride, or you found someone's like pass for work and could go into the company office. So hopefully that makes sense. I think this is quite different to how we think about defending things as software engineers. I think often we'll do things like scanning our code for vulnerabilities, checking that we haven't pushed secrets to Git repos. All that kind of stuff I think is really useful. But those are kind of automated scans. It's very different to this much more kind of active probing way that an attacker uses to look at a system. So with all this in mind, I'm now going to go through and hack a Flask app in a way that is completely based off one of the blog posts, well, one and a half of the blog posts that I read while doing some of the research for this talk. I'll go through these 4 stages. And the idea here is to sort of try and show you that you can do this to an app that you've wrote. It's not that hard. You maybe don't even need to run the commands, but just with some of this knowledge from reading a blog post, you can really see how someone might actually attack you in the real world versus just running a scan of your app. So just in brief, this is a very simple and very bad Flask application. All it does is accept a query parameter from the search key here, and that just gets sent into this template. So this render template function is basically just injecting this string. And I'm running it in a Docker container on my local machine. And this, well, I didn't want to do a live demo because they kind of freaked me out, but I did this earlier. But that's why it's on 0000 here, so I can forward the port 5000 onto my local machine. And I've done it in a Docker container because you'll see a bit later. There are some. I wanted to talk about how you can break out of a Docker container because I think probably a lot of us these days are running production applications in containerized environments in the cloud, in Kubernetes, and this is the kind of stuff, therefore, that I think is useful to consider how somebody might attack. So the first stage, there are probably a few things I'll just touch on briefly before you get to this point, is you're going to try and go through a list of all the endpoints, see what kind of responses you get back, and just kind of map out the environment. When you're doing that, one of the things that you would really like to see is an endpoint like the only one this application has, a search one, where as the malicious user, I can send something and you'll get something back that processes your code. How you might do that is then you would fuzz it. So fuzzing is you basically spam an endpoint with tons of payloads in the hope that one of them is a hit. It's like a spray and pray approach. And This is done here with a tool called GoBuster. I know this is a Python conference. Unfortunately, this tool is written in Go. I think everything else will be in Python. And this fuzzes stuff with a word list. So another really useful thing that hackers use all the time is something called a word list. In particular, this GitHub repo called seclists, I would really recommend checking out. It basically contains tons of, a word list is just a list of strings, tons of strings that are useful for hackers. So another example might be like 100 most common passwords, things like that. And here, all you're doing, all this tool does, is just send a ton of requests to this search endpoint, and it replaces fuzz here with every word that you have in the word list. And this is what the output looks like. It's probably a little bit messy to see. I'll go in the next slide in a bit more detail. But you can see we're getting lots of greens already, which is not good. So, well, good if you're the hacker, bad if you're us. And here you can see the kind of payloads that someone's trying to send in this spray and pray approach. It probably looks a bit unfamiliar in a Python world. I guess dir you would probably want to use on Windows command prompt to see if that gets you a hit. Who am I on Linux to see who's running? But we can see this gives us a 500 error. So this is kind of not really getting us anything useful back. It's just crashing the app. But it's a problem that it crashes the app, because really this should send back a 400 error. This is like a badly formatted request that shouldn't trigger a 500 error. So it's already doing something. And if we know that, if we're the hacker, that's good, because it means we can send something and get something back that is not what it's supposed to be. It's not at 400. And from there, I've kind of skipped over a few steps in the interest of time. What we then want to find out is, what is the right kind of payload to send to this application? So if we now know that it's running Flask, which would be maybe a reasonable guess if you're a hacker, a lot of things run Flask. I'm going to assume we just figured that out somehow in this talk. You can then look up, and this is from that repo I shared earlier, payloads all the things. What are the kinds of payloads that you send to the template engine in Flask? If you don't know the template engine, it's Ginger 2. And if you're the hacker, it's quite easy from here, because I can now look up someone else's work and see, OK, this is the syntax. Like if I send 7 times the string 7, I'll get 7 strings back. This is probably more familiar to us now. This is just like normal Python. And I know that if I get the result back based off what it says here, then I know I'm running Ginger. And once I know I'm running Ginger, I can then look for things to do nastier stuff. So this is what it looks like if, here we kind of copy the syntax from GitHub. We do 7 times 7. And we get 49 back. So this is great if I'm the hacker. I can now see, OK, you evaluated my code. The next step is going to look pretty funky, but kind of a lot more interesting, I think. This is some super weird code. This is exactly why I don't like hacking, because this stuff I find very strange, but it's kind of interesting. This now I got from one of the blog posts. This gets you all the objects that exist in Python from your payload. So this underscore underscore class underscore underscore thing, I think this means method resolution order, is going to give me a bunch of Python objects in a really horrible mess that looks like this. So this is basically everything that you could just like import in Python. I'm going to make that a bit bigger so you can see. And you can see here like token, instance method generator, like all these kind of built-ins. What's next if I'm the hacker? I've now done, technically what we've just done is called Ginger server-side template injection, because we're injecting a string that the server is processing. Next, we want to try and get access to the host. And to do that, because it's a web app, we need to open a new process to execute code on the host. So the Python object that does that we're looking for is subprocess.popen, so open a new subprocess. And that is what I'm doing in this next really horrible bit of code. The 342nd object was subprocess.popen. So once you've got that whole list, you can just process it, figure out which index subprocessor's in. And now, just to check this works, I have run a ls command. So this is bad. This is what is inside the Docker container, a main.py with some requirements.txt. So this is a kind of check that we've done that. So now we can do the next stage in those 4 stages. We're kind of fully done now with the enumeration step. Next step, if you remember, was credential harvest, the bit in my analogy of the burglar where you're getting the keys, or well, looking for the keys. And one thing that I think is interesting that I think I'm definitely guilty of, and I think as software engineers we tend to not think about that much, is every penetration tester I know runs env as soon as they get access to a host machine. It's literally the first command they run, just to dump all the environment variables. I think we're all super used to like 12-factor methodology, doing everything in environment variables. So it is really easy if you're an attacker to just get like API keys, usernames, passwords, because we so often store it in environment variables. And this would give you not very nice output. In my dummy app, I haven't got anything here, but I think probably a lot of us in production applications would have something like a Snowflake API key here, or something that, or like a service account credential in a cloud environment, which would be enough typically to, with a little bit of extra contextual information, like dump an entire database and leak all of your information. So once you've done that, the next stage is privilege escalation. This is a bit more advanced, this section, so I'm going to gloss it a little bit. But the main thing to bear in mind here is, suppose you're attacking something in a cloud environment, in a container. Again, I'm just picking that because I think that's what a lot of runtimes are these days. You might want to try and get to, say, the node in a Kubernetes cluster, something that, and then see everything running in that Kubernetes cluster. How you do that is you basically need to mount the virtualized file system on the container onto your own machine. So you need to basically tell it, hey, like where you're mapping on the host all of these files, give that to me. And that's what this bit does. You can run a command called fdisk here that will give you a list of all the disk partitions. Again, gives you a really horrible mess. But the final command is you do something like this. So you make a directory, I've called it pwned, just to be clear, and then you would mount the host virtualization bit that maps container files to host files onto your own machine. If that got a bit difficult and hard to follow, don't worry. The point there is just that we need to break out of the Docker container in order to get more privileges. And the real takeaway for this is that you have to be root on the container in order to do this. And it also wouldn't work unless you run the container with this privileged flag. So never do that. I don't really know why you would do that anyway. But the bit to remember for takeaways later is that you need to be root on the container. You obviously cannot look at disk partitions and change them out unless you're root. So just a quick recap before I move on to some of the takeaways. We've gone through enumeration. That was, I focused a bit on fuzzing there, and then sending a payload with Ginger to Flask. Harvesting credentials, we looked at getting environment variables for that, and then escalating privileges, we looked at how to break out of a Docker container and move onto a Kubernetes node. So now we've gone through that, what are some takeaways that you could do to improve your own security in light of this? So one thing that I think is quite easy is it's not that difficult to just fuzz your own application. There are a lot of tools like that GoBuster thing, which you could use to just send against all the endpoints that you have in a web app. Even if you don't really want to go through the trouble of downloading something else, you could just look at one of those payloads repos and make sure that all of your data validation for incoming stuff doesn't allow things like those curly braces that were essential for all the payloads. And I think your validation is just going to be better if you know actually what do I want to not let in. Something else you can do that I'll touch on in a bit is not store things in environment variables. Even though that sounds fiddly, there are actually some quite kind of well-tested ways of doing that in cloud environments. And then another thing you can do is implement least privilege for a container. So if it's not, very rarely does your web app actually need to run as root. So why are we typically running them as root? I think if I go on Docker Hub, almost all the default images look like they're running as root to me. So how do you change that? How do you make sure your container doesn't run as root? So this is how you can use Secrets Manager in GCP. Same thing exists for a lot of other cloud providers. You do need some environment variables in this example just for basic configuration, which I think is maybe a good way to think about this. I think environment variables are really good for configuration, less so for secrets. And then you make an authenticated call at the end here to actually get the secret, which means the secret is going to be stored in application memory. So if you're an attacker, it's really difficult to access something in memory. So that's much safer. This is more for reference, because I'll put the slides up later. This is a pattern for creating a Docker container in Python that doesn't run as root. You basically create a worker, install all your dependencies into a virtual environment, and then use a multi-stage build to copy that into the Nets container. But I'll put the slides in the Discord channel for that in case this is useful. Just to wrap up too, these are all the resources I use in this talk. So I really based this talk off these kind of blog posts that I was talking about. A lot of productive copy and pasting. And some fun ideas to finish off on. I think if you know this stuff, you can kind of hack hackers back. So we could send some fake response headers back to mess with them. We could say we're running a PHP app when we're running Flask. That would waste a lot of time. We could add fake SSH keys into our container. Again, it would waste a lot of a hacker's time. Everyone I know who works as a penetration tester is terrified of honeypots, but rarely see them. If you know what a honeypot is, it's like something that looks really easy to attack and might contain some juicy data. So like a misconfigured MySQL server. And you could just run that with fake data in a sandboxed environment and have it trigger an alarm if someone tries to attack it. Now you have an example of what vulnerabilities look like. I think that's something you could consider building. And yeah, that's it. Feel free to add me on LinkedIn and welcome any feedback.
Okay, first question. How do we sanitize the input before sending it to Jinja?
So there are lots of different ways of doing that. Probably my favorite way is with Pydantic. I think it's very good at input validation because it checks type hints at runtimes. But really, just doing anything is good. I think if you want a really basic way of doing it, you could just use a regex that only gives you like alphanumeric and kind of spaces or underscores. Most code needs like some kind of brackets or stuff like that to execute. Just that alone would help a lot.
Okay, thank you. Do you have any advice on how to secure NVARs without HC Vault?
Yeah, I mean, I think a lot of cloud providers have their own secret managers that help with that. I think people are often quite scared of doing encryption by themselves, but Python has a really great cryptography package that makes that not always that difficult. I would recommend digging into that if you don't really want to use someone else's solution. Fernet is a really simple encryption algorithm that is quite easy to get spun up yourself. Be careful where you store the key, though, if you do that.
Can we assess the security through fasting tests in CI? Can you advise any tool?
So I think it's really good to test security in CI, but I think you have to consider what works well for automation and what doesn't. So in my view, things like checking for credentials that are hard-coded is a really good use case for CI. That you can scan a whole app like that. People like GitLab and GitHub, I think, have put out a lot of kind of query languages for looking at overall application security. I haven't had the best experience with those. I think it's very difficult to like fully automate how someone would actually attack it. I don't think there's a downside to it, though. I don't think it really hurts.
Thank you very much. We don't have any more questions on Slido. Anybody wants to pose a question here?
one that needs a little context. It breaks the 160 character limit in Slido. So you went into an alternative to storing secrets in environment variables that it basically means change the code of the application. Now, sometimes we operate applications that we don't control the code base of. So do you have suggestions for more secure alternatives to running, to putting secrets in container environments that don't necessitate actual code changes?
Yeah, that's an interesting question. I think obviously it's going to depend a little bit on the environment where you run your app, but to give you one example, in Kubernetes, you could maybe try and, I think you can, in a pod YAML definition, change where you could read them in from a config map in Kubernetes and then secure that. So then you have some of the Kubernetes auth built in about who does it. I think that would be a difficult, I don't know if that's quite a Kubernetes specific answer, but maybe not, to be honest. I think that's quite a difficult problem. I don't know if any, yeah, happy to discuss that later, yeah.
So maybe a question related to that. If you already have access to the process running everything, then you also have access to the RAM and you have access to the globals, particularly in Python. So it actually doesn't really make sense where you get the credentials from. At some point you have to load them into RAM and into the globals somewhere in Python, and so you do have access, regardless of where you originally store those credentials.
Yeah, that's a very good point. Thank you for the correction. That is...
I didn't want to correct it. I just want to make that point because you can do lots and lots of, security kind of, let's call it theater, right? If you already have access to the process that's running the code, basically there's nothing much that you can do, right?
Yeah, so this maybe relates to, I think, quite an important principle in security, that it is rarely possible to make something like 100% secure, but I think you can add way more friction in, and I think that's a good thing to aim at. So if we think often that software engineers are lazy, I think hackers are definitely lazier, and it is definitely harder to get access to a program's runtime and memory than it is to just run an env command. So I think that would be a more accurate statement of the benefit of shifting away from environment variables into memory, that there's more friction, and so somebody's just more likely to move on and attack a different target that's easier. I think you also touched on another point that, like, I don't think as developers we should get stressed about making something perfectly safe, because we can't. But I think it's good to try and just make it annoying and difficult for someone to attack. Secure enough. Secure enough, yeah.
Okay, one more question from Slido. Do you have any tools that you can recommend for static code scanning?
I have a feeling Palo Alto might have bought something that I'm supposed to recommend, but I think GitHub QL I've used and I quite enjoyed. I thought that was good, and was like free to use on GitHub and my own kind of personal stuff. So I would try that out, see how it works for you. GitLab also have a lot of container images they do for that, where you can take a peek and explore a bit more what's in there.
Okay, thank you very much.
Everybody for coming back this session. Probably close that door. Yeah, thank you. This is Spaghetti Room, and we'll be having Mac talking about finding leaked credentials and how Python code could be used to leak millions of secrets. That's interesting. The only thing I have to tell you before we start, remind you that we use Slido to get questions. So please go to Slido/PyCon23 to get to Slido and select Spaghetti track to ask the questions. And so please give it a go.
Thank you for that, and welcome everyone. And especially thanks to everyone for coming to a security talk at a Python event. So I've got some depressing things to present, but hopefully I'll try and make it a little bit fun as well. So just quickly, a little bit about me. My name is Mackenzie, but I also go by Mac. I'm from Aotearoa, New Zealand, but now I live in the Netherlands, and I work for a French company in DevRel, and you can find me pretty much anywhere with the handles @AdvocateMac. And I'm also the host of a podcast called The Security Repo. My mum says it's great, so you should definitely check it out. It would be nice to have more than 2 views. No. Okay, so first of all, I'm going to be talking about secrets. What do I mean by secrets? This is probably familiar to everyone, but I'm really talking about API keys, digital authentication credentials, security certificates, credential pairs for databases, encryption keys, and anything that's really used to authenticate ourselves or allow us to ingest, decrypt, or post and send data. What's the key differentiator here is that these are made to be used from machine to machine, so humans aren't meant to type these in. These are meant to be used programmatically, but unfortunately humans touch them a lot. And whenever humans touch something, there's a risk for exposure, which we'll talk about. So very quickly, how do we use these applications? I'm sure everyone's familiar with it, but let's say we're building an application, and our application does a thing specifically. Maybe it's a social platform, and our algorithm is what's special about it. But it also has to do other stuff. It has to authenticate users, it has to post in a database, it has to be able to process credit cards. So we offload a lot of that to different third-party services. So maybe we're using Okta as authentication, Algolia as a search function, so on and so forth. So our application becomes a collection of different services. These services leverage secrets to be able to communicate. As an attacker, as a security guy, every one of these icons, these logos, is some way that I can get into your systems. But then once we've built that, we need to host it somewhere. We need to host our code. We need to test our application. So now we have a lot of infrastructure we have to deal with. All of these communicate with secrets as well. Once we launch our application, then the pesky marketing team and sales team are going to want integrations into different areas. And again, more integrations. And we haven't even talked about the hundreds of microservices that we've probably built that we're communicating with that also leverage secrets. So very quickly, our applications end up into being these collections. So that's the kind of the recap of what it's. So hopefully we're all just on the same page here with what I'm going to be talking about. So one of the things we do at GitGuardian every year is we release this report called the State of Secret Sprawl. And basically, we look in public places to see how many of these secrets we can find. And then we release our findings. And I'm going to talk a little bit about this report, and I'm going to focus in on what we've found in relation specifically to Python codes. So you're probably all familiar with this site. This is GitHub, the largest code sharing platform on the world. If you want a collection of the most amount of source code ever, then GitHub is where you want to look. So just very quickly, I'm going to do a very quick demo here. Okay, so I have here a public GitHub repository. And I have here some AWS credentials. And I just have it in a file called config.py. And I'm going to do the biggest sin that you can do in programming, and that's commit credentials to a public GitHub repository. So we're going to make this. Now, the reason why I'm doing this is these credentials are what we call honey tokens. So what these credentials are going to do is they're going to alert me anytime someone tries to exploit them. Anytime an attacker tries to use them, I'm going to get a notification to say, here's the IP address, here's what they're trying to do. At the end of my talk, I'm going to show you how many people between now and then have tried to use those secrets. And I'll explain how they've found them. So hopefully the bad guys are up out of bed, ready to go. And well, otherwise it will be a little bit embarrassing, but I'm pretty confident. So just while we're talking about GitHub, how big is GitHub? It's very big. There was over 1 billion commits last year made publicly, just publicly. There was 85 million new repositories made, again, just publicly. And according to GitHub, there's 94 million developers using it. So this is an actual fire hose of information. And lots of weird stuff ends up on GitHub. Code that's meant to be private makes its way to the public repositories. It gets shared in different repositories. So you can find a lot of interesting things on GitHub. So what we did at GitGuardian is last year, we scanned every single one of those billion commits for secrets. So we scanned it for 350 different types of secrets. And then when we found the secrets, we validated them with the providers to make sure that they were actually valid and real credentials. So how many secrets did we find on GitHub? We found 10 million. 10 million secrets, which is about a 67% increase to last time. So these are secrets that are hard-coded or files like configuration files that have been included in public repositories that anyone can access. And so to give you an idea of numbers, 1 in 10 of the authors that pushed code publicly last year committed a secret. So that means that there's probably about 20 of, or maybe not 20, maybe 10 of you in here that pushed a secret last year according to these numbers. So it's not a problem that only affects a small group of people. It happens all the time, and it happens in kind of weird ways. But it's a fairly big problem. The number one place that we found secrets, anyone want to take a guess, is in the file extension .py. So app.py, config.py, anything like that. Now, this doesn't mean that Python developers are worse than everyone else, because you'd probably also know that Python's the most popular language on GitHub. Therefore, more code, more secrets. Makes sense. But it is showing that it's definitely a big problem. So it's not, if we look at some of the other files too, it's not just .py files that you might expose it. If you're using JSON or envs to manage your secrets, you could have a Python application and leak it with these file extensions as well. Lots of different files that we actually found. Just the .py, we found about 2.1 million secrets in just Python files. And there was about 1.3 million files that we found those secrets in. So again, this is an absolutely massive kind of scale of problems that we're talking about. What are the actual secrets that we typically find? So about 25%, 2.5 million were for data storage. So Amazon S3 buckets, could be managed databases. We also found about 2 million cloud provider keys. So what I just leaked on GitHub is for cloud providers. These are pretty scary because they're easy to validate. And as an attacker, yes, I can disrupt your infrastructure if you leak I can move in, I can do lots of nasty stuff. But even as a script kiddie, I can just do crypto mining on your accounts and rack up a huge bill for you. So you don't need to be very innovative to be able to figure out what you can do with a cloud provider key. Messaging systems is another one. We found huge amounts of things like Slack webhooks. And these are really interesting as an attacker because you may not think that they're that sensitive. But if I can post messages to your internal Slack channel, pretending to be you, saying you need to update your password, then that's a barrier of trust that a phishing campaign might not be able to get. So they can be quite sensitive, even if you don't really think that they are. And we've found a lot of personal projects where people were building Slack bots for their work. Maybe they get a notification when something goes down. They've been doing this on their personal kind of time, so it's ended up in their personal GitHub account, but it gives me access into your company through ways. So quite scary. The one I find funny is we found 3.8% of what we found were version control platform keys. So basically, we've found the keys to access your private code inside your public code, which was fun. We even found 500 commit messages where the message was your GitHub authentication credential. So it's kind of like you've sent an email and the subject is your password. That's kind of like the equivalent of what that is. What about Python specific? It's kind of hard because we find such a long list of different secrets for different services. But, Google API keys was number one. GitHub access tokens, AWS keys, lots of different kind of things in here. All right. So now I want to talk about how attackers actually do this. If I'm an attacker, I'm looking for these, I've just leaked credentials, I'm hopeful that someone's going to find them. How does that person actually find those credentials? So there's lots of ways. This is the most obvious way, and one that's not that great, but I'll talk about it anyway, and that's just using the GitHub search functionality to be able to find files, right? So here I'm going, file name is credentials, and I'm looking for AWS access key. The search format is actually updated since I made these slides, but it's the same thing. Now you look for a path instead of a file name, but you get the idea. And there's lots of these that you can get called GitHub dorks where you can copy them and it's looking for sensitive stuff. This isn't that effective. One, you're going to have to sift through a lot of information. And two, what I want to stress, and I'm going to bring this up again later, is that when we're talking about Git, when we're working in Git, everything we do is version controlled. You leak a secret and remove it later, it's still in your history. So the GitHub search functionality doesn't look in your history, it just looks at the top layer. But the history is where you want to, it's really where you find secrets. So there's a much better way of finding secrets, particularly on GitHub, and that's abusing the GitHub API. So GitHub has a public events API. You just go to api.github.com/events. Anyone can do this, and you don't need any authentication. Now, what's scary about this is that this is a public ledger of everything that's happening on GitHub in real time. So everything that's happening, anyone can see on this ledger, and they can see your email address, who you are, and they can even find information about where you work. So they can monitor you. When we talk about things being public in GitHub, we understand that someone can go to and find our repository, right? We understand that. What we may not understand is it's actually being broadcast. All that information is being broadcast, and that's why the credentials that I just leaked are now in this ledger, and there's a bunch of bots and other things that are sifting through it and looking for them. And there's lots of events that are published in here, but the two that the attacker is going to be after is a public event. This is when a private repository goes public. Remember that it brings its history with it. So this is by far the most interesting. This is where you're going to get the best results. And then the push event is just when code is pushed. So these are the two ways that you can discover secrets. So does this actually happen? Are there breaches because of this? Yes. This is an example that happened last year. It's not a critical example, but it's interesting. Toyota, they have a mobile application called T-Connect, kind of important, can start your car. And what actually ended up happening is they were working with a contractor on this project, this T-Connect, had a Python backend. That contractor accidentally made their code public unknowingly. Inside that code was credentials for the database of all the users. Attackers, threat actors found it and were then able to launch phishing campaigns on everyone in that database because they knew they had a Toyota, so they could customize the campaigns and spam them that way. Luckily, security researcher also found it and alerted Toyota before anything too bad would happen. But this is just an example of when actual stuff does happen because you've leaked your keys. Now, the other area that I want to talk about is probably you're sitting there, okay, this is great, interesting, thanks, Mackenzie, but we don't have any public source code. Everything we do is private. I have no public source code whatsoever, not relevant for me. It doesn't matter because source code is really bad at staying private. It's an incredibly leaky asset. Think about everyone in your organization that has access to your source code. It's on their computers. It's probably backed up in different areas. It's inside your wikis, it's inside your documentation. So it's very prone to leaking. So if you're relying on just the authentication in your GitHub, then it's going to be very insecure. And last year, we saw lots and lots of secrets that were leaked publicly. Microsoft, NVIDIA, Samsung, Twitch, all of they had their source code, let's say involuntarily open sourced, mostly by a threat group called Lapsus. They were purchasing credentials on the dark web. They were hiring insiders to gain access to this source code. So it wasn't a very sophisticated attack that they were doing, but the source code was able to make it online. So your source code is never an adequate place to store secrets ever in your history and that, because if it makes it public, then it's out there in the world, and threat actors are really targeting developers specifically. So we just take a look at one of these, Twitch. They had their source code leaked. There was 6,000 repositories that were made public. It was available on a torrent. It was made public because there was a misconfiguration in the Git system. They were managing their own Git server. They accidentally just made it public. It was only public for a few hours, less than a day, but still in that time someone managed to scrape all of it and publish it. We found 6,000 secrets inside that source code, including 194 AWS credentials. So pretty significant breach, and this isn't that bad. This is typical of what we'd find in a large company like this. So it's a real problem that's affecting a lot of people. Another breach here, I won't go too much into it, but Uber had some pretty bad ones. Essentially, if you know what a PAM system is, a privileged access management system, it's basically a secrets manager and a password manager rolled into one. If you don't want a threat actor to have access to anything, it's this. It's the most sensitive thing that you have because it creates accounts on all your services. They had hard-coded the credentials for the PAM account in a PowerShell script and version controlled it. This PowerShell script, what it did, when a new employee came, they ran this script to create them accounts on what they needed. So if it's a developer, I'd create 100 accounts for all their tools that they needed. Because they had hard-coded that and version controlled it, it was in their Git history. A threat actor, again associated with Lapsus, made it onto their repositories, found this credential, and was then able to create accounts for themselves and everything. Fortunately for Uber, they weren't very malicious. They were more after the clout. They were posting inappropriate things in the Slack channels, for example, when they got in there. They basically just wanted to say, hey, we hacked all of Uber. But Uber could have been shut down for multiple days because of this, had they wanted to. So just another quick example. Are people here familiar with Docker? I'm pretty sure, yep. I forgot where I was for a minute. Docker is another place we find lots and lots of credentials. I won't go too much into it, but basically we scanned tens of thousands of Docker images. We found that about 5% of them contained hard-coded credentials. A lot of these credentials were for things like package managers, but it means that we could poison your applications from this. So the secrets are not only just finding their way into version control systems and Git, it's also Docker. And I want to give you a quick example of a massive attack that happened because of this. So this is a company called CodeCov. Maybe you've heard of it. Personally, I like CodeCov. I think they're a great company, but they had a pretty significant breach. CodeCov is a code coverage tool. It tests how much of your application is being tested in the CI/CD pipeline. So it does a specific thing, not that critical, but important. The official Docker image for CodeCov had a leaked credential inside it. This credential allowed them to modify some code. So it allowed them to modify the bash uploader script, which was being hosted in I think it was a Google drive somewhere. They poisoned that bash uploader script to do one thing. It said, whenever you're running CodeCov, I want you to dump all the environment variables and send it to me. So when your application is being tested, it needs to be built. So you need credentials to be able to do this. Hopefully, you've got test credentials, not production credentials, but you also have things like your GitHub access credentials. That's what the attackers were able to find. So they then poisoned CodeCov, thanks to this. They had 20,000 users at the time, and the threat actors made it into the private source code repository of all of those companies. And there were big ones, Twilio, Monday.com, HashiCorp, all had their private source code accessed by threat actors because CodeCov leaked a credential and then that allowed them to poison it. I almost never pick on companies when they have breaches because frankly, I think it can happen to everyone. But I'm going to pick on a company. So HashiCorp was part of this. So if you don't know what HashiCorp is a fantastic company, and they build, in my opinion, the best secrets manager available. HashiCorp Vault. Very heavy, but it does a lot of great things. They coined the term secret sprawl. Their whole thing is about keeping secrets outside of your source control. Because of this breach, they had to report that that the threat actors had found a secret in their source code and been able to use it. If HashiCorp has secrets in their source code, there is no hope for anyone else. So this just shows the scale of the problem that we have here. Other examples too, hard-coded credentials for a bank allowed them to access thousands of checks. I don't have time to go into it, so I'll just skip past. But secrets find their way into mobile applications as well. I've done research into mobile applications, and it's a terrifying place there. So let's get into why does this happen? All right, no one here is stupid enough to put a hard-coded credential in Git, right? No one here would do that. So the first thing, we need to talk about Git history and how this all works. Let's say, so in this round, we've got a feature branch in Git. I'm sure everyone knows what I'm talking about. I say to you, hey, here's some Algolia keys. I need you to connect to it and test. So as a developer, you go, I'm just going to quickly check the connection works. I'm just going to pull some information. Cool, done. Okay, I'll remove those credentials now. I'll put them as environment variables or however we manage to do it. But you're just testing it. So they've removed the credentials, and let's say you get 100 commits down the path. It's time to have a code review and pull it into master. The reviewer, well, I don't know about you, but I'm not going to look at 100 commits at all the mistakes you've made to get to this point. I'm just interested in what you've done. So I'm going to compare that to my main branch, and I'm going to merge it in if all is good. There's a secret in there that's still in your version control history, but no one knows it's there. So this is one of the reasons why this is such a big problem. Other reasons are in logs and auto-generated files. You do a debug. You do a debug that's going to sometimes dump out your environment variables. There could be secrets in there. Git add all, because I'm lazy, and that's now in your Git repository as well. Not having .git ignores. This is one of the, in terms of like preventing them getting into Git, everyone should have a .git ignore file. Please do. Putting secrets in the secrets.txt because it's a pain to get them, and then accidentally adding that. Secrets and template files. So when you create a Django project, the secret keys are in there if you don't remove them. Now Django's updated how they do that now. I think they say test credentials or something like that, so it's a little bit better. But that's just one example. There's plenty of things. If you connect to a Google service like Firebase, they're going to give you a downloadable file so you can get quickly moving. But unless you take a minute and handle those secrets properly, it's going to be an issue. And then just sharing them on Git. It's easy, right? There's only 10 people on the team. Let's just put them in. Let's put the env file in Git and be done with it. It's protected. So we see that a lot. We see everything. And then, of course, just hard-coding credentials that we've talked about. So lots of reasons why this happens. Now, I don't have time to go into it, but this is where I get controversial from the other security guys because managing secrets is a level. Every security guy says you need to be on level 4. You need to be using Vault, dynamic secrets, auto-rotation, everything. And my argument is you need to do whatever you're actually going to use. So that might be using a Vault. If you're in a large company, that might be. If there's 5 of you working on an open source project, maybe encrypting them and putting it in Git is okay. As long as you don't keep hard coding them, it's a win, in my opinion. So just very quickly, some tips. This one should be obvious. Don't do it, not even for testing. Never hard code your credentials. Now the other one here, there's a Python project called .env. It helps you put them into Python.in helps you put them into an environment variable file and loads them in. So putting them in a .env file can be great. It centralizes it. You can protect it with your .git ignore as long as you know it's there. And then you can use a project like Python.env to load them into your local memory and use them. And then you'd never have to hard code them into your source code. So that's a cool thing. I have a whole video on how to do this, but it's more aimed at beginners, so probably not anyone here. But if you do want to check it out, it's on the Git Guardian YouTube channel. And the other one is that I just really like to stress this. Use whatever you're going to use, but actually use it. So maybe that's Vault, where you're auto-rotating, it's dynamic, you have a secret server, you need 3 people to manage it. But maybe that's, if you're in a company of 400 people, you should be doing that. That's absolutely what you're doing. Maybe if you're a little bit smaller, maybe using other secrets managers, a little bit down the crowd, when your cloud infrastructure will have some features that they can use. And if it's just a small group, then you can encrypt them with certain projects and store them in Git if you want to. Nearly everyone will tell you this is a bad idea, and it kind of is. It centralizes your secrets, gives you a single point of failure. There's lots of reasons why it's bad, but if it means you're going to encrypt them, it means you're going to do something, then just do that. Automated secrets detection. I work for a vendor. We got fancy tools, but there's also open source tools. And if you don't trust me, there's more open source tools there. use Git hooks. Rotate your secrets regularly and have a policy, so then you at least know how to do it. Limit your privileges. If an API key only needs to retrieve data, make sure you set it so it can only retrieve data. Don't publish admin keys and whitelist your services. So I'm out of time, so I won't go any further, but I do just want to have a quick look at the experiment that I made. So here I said this is the key that we published, and if we look here, we have more. We have 13 times that key's tried to be exploited since I've been talking. So if you look at the timestamp here, these are the IP addresses of the attackers. This is what they've been trying to do, and this is basically how they're trying to find it. So TruffleHog, for example, is an open source tool. So leaking a secret in public repository, bots are looking for this. It's going to be found. So it is a big problem. And with that, I'm out of time. If you want to look more into the reports, the state of secrets rule is there, and that one's a model on how to manage secrets if you're interested. And thank you very much for listening.
Thank you, Mac. That was amazing talk. We have plenty of questions. I'll try to be very quickly. The first one is, have you notified the user or used all the secret discovery?
Yeah, we try. So in the commit metadata, there is an email address there. Now, it can be a no reply email address. It's configured locally. If that email address is there and we find a secret and we validate it, we will send them an email from GitGuardian and say, hey, you've leaked a secret publicly. But we can't do it for everything because some secrets we just can't validate. And we don't have enough confidence that it's not a false positive, and we don't want to spam people. And some secrets, and some people just don't have email addresses. So we make an attempt. I think we were able to notify probably about 30% of what we found of that 10 million.
Questions keep coming, so I'll be very quick. Is there any convenient way to scan your own code base for secret leaks? It's not on GitHub, this one, but it's on GitLab and has Milia's integration.
Yeah, there's lots of ways to scan it. So there's open source tools, if that's appropriate for you. TruffleHog, GitLeaks, GitGuardian, the vendor that I work for. We are completely free for anyone with less than 25 developers. We integrate into GitLab, and so we can do a historical scan and uncover secrets. We also have an open source tool called GG Shield. So we can definitely do it, but if you don't trust me and you want to use open source tools, there's plenty available that will connect in there. It's a little bit harder. With GitLab, you can put it in the pipelines and things like that. So there's lots of ways to do it, but yeah.
Loving the talk, kudos. Do you typically look for specific credentials, for example, AWS, GCP, or also for general custom password?
So we do both. So something like an AWS credential is prefixed, a certain amount of characters, so easy for us to find. So we can cast a much wider net, and then we can validate it. So it doesn't matter if we get lots of false positives in our initial scan, we can validate it. And then we also do generic secrets. So, general high entropy strings. This is really challenging because a high entropy string has about a 5% chance of being a secret, and the other ones will be like a unique identifier. So what we do is we find all the high entropy strings, and then we will search through the code automatically to try and find out how much references I can find to if this is a secret or something of a test. But with generic secrets, because we can't validate them, and it could be like a test credential or something, then we get some false positives. But we try, it's much more of a challenge because we have to do a lot of post-validation to try and figure out what it is automatically.
I'm going to ask you a couple of those very quickly, and I'm afraid this is going to be the last one. Does Squash on merge prevent the secrets being exposed? And the other one is there any way to clean the Git history post-incident, or some suggestion to prevent this?
Okay, yep. So Git Squash, Git is very tricky. Lots of stuff with Git is reversible. So Git Squash is reversible. You have to do a garbage collection to be able to make sure that that's actually gone. So I never recommend doing that. The reason is because you can't be sure it's gone, and also because it's bad policy, and also because history's there for a reason, right? We should maintain our history. So if we go back, we can see why we made certain decisions in areas. Getting rid of your history limits you in other ways. So it's better to do it. Now with the cleaning the history, if a secret makes it into your repository, there's no other solution but to revoke that secret. You can try and hide it, but you have no idea where it is. You don't know whose machines it's on. You can clean history. I have videos on this as well. There's a tool called BFG Repo Cleaner, I think. There's some other tools as well that you can actually go in and pick out your secrets. But if you do leak a secret, please, please, please just invalidate the secret, issue a new one. If you have to tell someone at work that you've done it, like, it's forgivable. But if that secret will haunt you. And just like how these all work, the secrets that were scraped from GitHub, they were all bots that found my credential. But I'm going to get a peak of activity for the rest of the day, and then there'll be nothing. And then in 2 weeks, 3 weeks, or a month, I'll get another peak. That's because that credential has been sold on the dark web. People capture them, they sell them, they'll sell 1,000 valid AWS credentials, and then another threat actor group will try and exploit them. And maybe they'll squash it down to certain companies and areas like that. So if it leaks into your Git, even if you haven't got any notifications now, I mean, you just never know where that secret's going to end up, and it will end up somewhere.
Brilliant.
Thank you.
I'm afraid that's it. Thank you so very much, Mac, for the talk. Will you be around?
Yep, I'll be around.
Okay, so
yep.
Catch up with Mac, and we'll reconvene in 20 past. Yeah, I spent too much time talking about spaghetti because we are in spaghetti, by the way. So this is just to remind you that we're going to take questions on Slido, and spaghetti is the room. Thank you very much for closing the door. So it's an extreme pleasure for me to introduce my friend Adrian. He's going to talk about a very interesting project. I don't want to give any end or anything, but it's absolutely cool project, and the talk is going to be amazing, I'm sure. Otherwise, you know what will happen to you. Before starting, what I want to say is Adrian is very happy to take questions during the talk. So if you have questions, post them on Slido, and I will make sure to ask them the question. All right? So please give Adrian a big round of applause.
Thank you very, very much. I'm Adrian. I've been working on this project, but I mostly would like to talk about pickle stuff. It's always fun to see how bad something can be. It's great, but not bad, insecure. Bit about me, I got my PhD in bioinformatics, but it was machine learning in bioinformatics. I forgot the bio side, ended up doing ML consulting, ended up working like as somebody who does algorithmic privacy and fairness. And most of my time I'm doing open source, either working on scikit-learn or fairlearn, or these days a lot on SCOPS. So let's jump into it. Let's have fun with pickle. What do you think like this would do? I'm loading a byte array with pickle. It's just like a simple byte array. What it would do is that it returns 0. So if you put that in a variable, it returns 0. But it prints something in your console. And it's not like a Python print. I'm calling, it's a POSIX call. I'm calling like echo something. So this simple, just loading this byte array does something that you definitely do not expect loading pickle should be doing. What this does is that it relies on OS here being available, and of course it's available. You could try to circumvent that. The pickle machinery allows you to subclass unpickler, and when you do pickle load, you're basically instantiating the unpickler, and then like you read the file and you do whatever you want. And a method which you can override there is find class, and here you can have something like is it safe? If it's safe, sure, return that. Otherwise, raise an error. It would make, so if you have like a custom in-house loader that you get a lot of pickles from around and you're loading them, it would be a good first line of defense. There are a bunch of things that you eval, exec, these are the things that you probably don't want your pickle to be doing. The issue is here, this is gonna be in your globals. Like in Python, you have this thing, globals, that like stores everything that is like available to everybody. While loading pickle, you can modify globals. So what you can do is that you have a really nice, nicely crafted pickle file that changes the values in this thing and then loads what it wants to load and does what it wants to do. And there are like attacks that can show that even if these two are two different processes, like you send to a different process to check something is valid or not, you can like even modify that. Like there are very sophisticated attacks. We're not going to go through those today. So because of the way that pickle works, at some point, and this point is like quite in the past now, Python used to have this thing like safe for unpickling and safe constructors kind of thing that like you would be like, no, these are safe, but then very soon people realized that no, they're not. So they decided to just like remove that whole thing. That was removed for Python 2.3. And after that, we know pickle is not safe, and everywhere that like there's a pickle, you should have this warning that do not load any data from any source that you don't trust. So how does pickle work? In short, you have these three things around pickle. You have the pickler, you have the unpickler, and then you have the instruction set and the pickle machine, and like basically your opcodes. So when you're loading pickle, you are running code. It's not like you're loading JSON. You run code, and at the end, you would have a variable like in that machine, and you return that variable. That's like how like unpickling works. For most objects, what is important there is like how does pickle know like what should I store and how should I load? The two most important methods would be getState and setState. These are like two of the magic methods for like Python pickling, and let's have a little bit of fun with that. Here I have a class. The only thing that getState does is returns a dictionary, and in setState, whatever dictionary I have, I just set the attributes on self. So now I dump this and then I load it, a completely empty class, but once I load it, I would have this thing. So you could do a lot in your getState and setState. And if you look at the, like you can try to look at like the pickle and you can see that, yeah, like here I have like a class from module main. And then here I'm setting this A, it's 42, and I pass that to setState. That's how like it's done. And I can save this and load it. It works. This object that I loaded does have that attribute, but it works. But does it really work? Let's try to load that in a different kernel. It raises an error because as you see here, it tries to import C from main, and then of course you don't have it. That's why you can't pickle classes that you just have in like your kernel now, and that's why Cloud Pickle exists. Like with Cloud Pickle, you can like pickle these things, but that means that you're serializing code, so it gets even worse. So the next one, which is the real evil one, is reduce. Up until now, we have assumed that like the constructor is a normal constructor. The especially the new method, like the dunder new method, is like a normal new method. We haven't overridden that. But if you do, then you would have to implement reduce. It returns a tuple of size up to 6. The first 2 are the mandatory ones. The first one is a callable that is supposed to be called to construct the object, the initial like value of the object before like the get set state. And the next one is a tuple argument to pass to that constructor. This way, this is how everything in Python can be pickled and unpickled. If you write a custom C extension type that you want it to be pickleable, you implement reduce for it, and you call your constructor, like it works. But this means pickling, like here I can have like whatever I want. So in reduce, I could print something, and if I look at it, I see that from built-ins I have print, and I'm printing something. And if I load it, I get that same thing. But because the way it works is my constructor here is print, and I'm passing a string to print. I'm telling pickle that like you need to call print to construct my object. Well, you could call a lot worse methods here rather than print. So like you could do like whatever you want. Here, for example, I call a system call and I write a file. And if I unpickle that, it writes the file for me. Just like the fact that I load it, like I don't see anything, but the side effect of that is that I just wrote a file with an arbitrary content. So I get a pickle from somewhere, I load it, and you can add this thing at the beginning of your pickle. Like pickle doesn't constrain you to have like only one object. So you can have this side effect and then return a legitimate object, so the user wouldn't notice that there something odd happened, but something is modified like on their system. It can be as bad as you doing a reverse tunnel to a remote server that you want to have. And there are like a lot more attacks, like a bunch of like attacks are like on the like category of denial of service, like unhandled exceptions, protocol downgrades. Like you have different pickle protocols, you can like play around with them. But there are also some weird stuff. Like there is an opcode DUP. It duplicates the top whatever is top of the stack. The pickler never produces this opcode. but the unpickler and the pickle machine understand this opcode. So one thing you could do, you can have like an unpickler that just like refuses this, because like if you have like DUP in your opcodes, like somebody has done something funny with your file. And there's a lot of like other like parser abuse and stack corruption issues there. Any questions up until now?
Adrien, well, when the new object in Python is constructed, the dunder new method is invoked. How dunder reduce method is linked to this in this chain? Because when you call and exploit it, what is the sequence that is executed?
So if you have a new method that has an argument which is mandatory to be passed, you need to have a reduce method which returns the new method as the constructor and whatever is needed to be passed to new as the arguments that are passed to the new. That's exactly like the only two required, the two first members of that tuple that is like 6. The first one would be your new method, and the second one would be the arguments to that new method. So if you have like a kind of a custom fancy new, then you probably also like need to implement reduce. There's like also reduce X. The pickle machine here is a little bit more complicated than like what I'm presenting here, but with just reduce you can do that. And it's the same, so there's no difference between new and if you have a C extension type, for example, if you write code in Python, if you have like your fancy constructor, then you would have to have reduce. The way Python, I don't know like how much you know Python, but the way Python generates C code for your kind of like Python looking code, the way that works is that if I have a C extension type in Python and if I have a C constructor, if I don't have a C constructor, it generates a reduce for me. That's how most Python classes can be pickled. But as soon as you have a custom constructor in Python, it does not generate the reduce for you because it doesn't know exactly how. Then you have to implement that, otherwise your object cannot be pickled. All good? So some of the things we could do is we could look at like how this pickle looks like a bit better than just looking at these like opcodes. You can try to generate the AST of the code that would run to generate the object. For example, here the thing that I'm dumping is a list 1, 2, 3, 4, and then here I know that I'm storing something in this result that I am returning at the end, and the values are it's a list, and the elements are these. Looks pretty benign. I could look at this and be like, yeah, sure, I can load this. Looks safe, I guess. But note that in order to do that, I already called load. So, and then let's do that with this class that we had up there. And when I do that, I see that it is calling something like from module POSIX. If I was in Windows, it was probably like loading something else. And then it is calling system and then echo something. So I look at this and I know something shady is happening. And then it puts that into this, and then it copies that into this, and it returns that. And that's how like it works, because like these intermediary variables, you can have as many as you want when you generate your pickle file, like, and some of them you can just ignore. There is no tree structure per se, which is also helpful because if you have pointers between things, that's why not having a tree structure kind of helps. You just have a bunch of objects, and at the end you construct what you want to have. So let's. Oh, so there another thing that like helps is this library called Fickling. It also has this. You can call it, and you can pass it a pickle, and it gives you the Python code which would generate the result for you. You can look at it. It's nice. You can investigate some of them, and like if something bad is happening, you can like pretty easily spot. But let's say like something like a more realistic kind of use case. I have a logistic regression. I dump that, and let's look what fickling would give me. The result would be a little bit longer with a bunch of like byte arrays, and you don't necessarily, like, it's not easy to tell now if this simple pickle file is safe or not. So up until now, everything was like completely like library agnostic, applies to all Python. But me being one of the maintainers of scikit-learn, we were like, okay, what can we do for users of scikit-learn? So now we're going to talk about some of the things that we've worked on in order to be able to persist mostly scikit-learn objects. You can persist other stuff with it too, but our focus is like scikit-learn objects. Any questions up until now?
Who is having the question?
Yeah. I was just wondering what happens with joblib format. We use that for these models and stuff.
For most cases, joblib is pickle. There are some optimizations on joblib for like if you mix like joblib with Loki and like or like Dask, like all of those things, like it can be much faster than just using pickle. But there's no pickle vulnerability that does not exist in joblib. And there are more vulnerabilities in Cloud Pickle that exist in Pickle. If I'm not mistaken, some of the stuff that like in the older days were only in joblib, like especially like very specific to NumPy arrays and stuff, in the modern Pickle protocols, they have become obsolete because modern Pickle does the same thing.
Good to go.
Cool. So we started working like, putting this work in scikit-learn itself would be not that easy. So we started like a separate library, called it, I thought I'm calling it skops. People ended up calling it scops. Sounds more fun. Fair enough. And apparently it's also like an evil character from anime or a video game or something. Happy coincidences. It has this like scops.io. It exposes pretty much the same protocol as Pickle. You can load and dump objects, except that most things we're like, we don't know this thing, we can't load it. And the user has, it's not like up to the library. The user has to be explicit, like they're like, which is also like in line with the scikit-learn philosophy that explicit is better than implicit. It is annoying sometimes. User has to do more, but they know that they're what they're doing. And in this case, I am supposed to be loading main.d. Definitely don't know that. Definitely not doing it. But you can say like, I actually do trust that, and it loads it. Or if you really, really trust the source, like it's yourself, then you can say like, I actually trust this file, load it, and we load it. Let's look at some examples of dumped files. So here, I have a class C. It's from module main. So the issue that if you do not have this C in your main right now, loading would fail. It failed in Pickle. It would fail here too. Like no difference there. And then the rest we call getState and we save that, but we do not call reduce. So if you have like some fancy reduce, it just doesn't work. Loading them, therefore, like loading them doesn't run those codes. If I have, for example, this one, this was a little bit more shady. It was doing things, and you see that like here, I just don't have any of those shady stuff because I'm just like not calling reduce. But if I look at the linear regressor one, it gets a bit like it's more complicated. My schema does include a lot of stuff. Sure, it's linear regression from scikit-learn. I call getState. One big difference is that if I encounter a NumPy array, I don't bother with trying to store it my own fancy way. We call NumPy save. With a catch. Oh no! I closed my Firefox. Does anybody know? Is it there? Yes, it is there. We recovered from disaster. Where was I?
Adrian, and what is the content of the of this NPy file? Is it a reference or what is inside? Because the CLFs, when you export it, when you pickle it with scopes, you said that this the NumPy array there was no content. It's referring to a file.
Yes.
Yeah,
So
and what is the content of the file?
So here, like the schema. So basically, the scopes file is a zip file, and we just like in the schema we store the name of the file that includes the data for that thing. And here you have a bunch of NPY files. This is what we load. Like we just like call NumPy load, and then we attach that to the variable that is supposed to be attached to.
So that's there's an array, I guess.
Yes, in this case, like it's an array. If it's a NumPy D type, we just like use NumPy save. We do some hacks. For example, an attribute can be a D type. How do I store a D type? We didn't bother with like finding a way to store D type. Store an empty array with that D type, and then load that array with that D type, and like read the D type. Like that's like kind of like a hack that we're doing around that. There's a catch that NumPy save, if there is a D-type object in your NumPy, it falls back to pickle. So what we do here is that we specifically pass allow pickle false, and if there is an object D-type, we kind of assume that kind of like a list of Python objects, and you do your recursion, you're like, please now try to persist this list of NumPy objects, and we try to persist those like objects. The same with NumPy load. The good thing with NumPy load is that by default, allow pickle is false, very reasonably so. So if you have like a NumPy with D-type object, you do NumPy.load of the NumPy save, it fails by default, because there is a pickling happening in between. And then you can just load it. In this case, I don't have to pass any trusted values because we have tried to have for most of the sensible scikit-learn, NumPy, SciPy types to have them like kind of trusted by default. Again, the same issue happens if you have some malicious code that before running this is changing those global variables and trusting things that shouldn't be trusted. Then you're running malicious code, but loading the file doesn't run those codes. So because when we load the file, we just, I'll talk about that later. That said, like if you do have a malicious library installed, you're out of hope. Because if you have a malicious library installed, running Python runs arbitrary code. Just you run Python, you run arbitrary code. So we assume that you do not have any malicious libraries installed. And the way it works is that we call new. So if you have a fancy new implemented, it just doesn't work. And for the few objects in scikit-learn that they do have like this fancy new, instead of like we try not to like rely on the get on reduce, we just like have custom classes that save and load those objects. So if you have custom objects, this format wouldn't work for now. And this is kind of the limitation. Like you don't work for everything, but at the same time, it's like you get a little bit of security out of it. We only work with like get state, set state for pretty much everything. And we have like special treatment of like certain types like dict, set, list, tuple, type, slice, all the like NumPy, SciPy, ufuncs. There are some C extension types that like require calling the reduce. We do that, but we only do that for those classes. For everything else, we just don't. And the loading process, we load everything from the schema file into memory without constructing anything. Then we investigate like what we are going to load, then we load. So any attack here would be any JSON load attack. So if you have a vulnerability on JSON load, then sure, it's vulnerable, but otherwise, it's okay. And then we create an instance with new, assuming there's no funny constructors or like arguments there, and then we call set state. If you want to try things, we also have an online thing where you can, if you're using the latest scikit-learn version, you have a pickle file, you can load it here, you can convert it, it gives you the converted file. You can definitely uncheck that if you don't want us to have a copy of that file. Is it safe? No code is 100% safe. Would I use it? Yeah, we have been using it. It works. It's nice. Is it fast? Definitely not. That's not the goal. The file, like the latest released version, the zip files can be also pretty large. But now, like we're gonna do a release. We expose the compression arguments to zip, so you can compress your zip files. Like that helps a lot. There are some raised exceptions. Make sure, like one of them is that like if you try to load something that has untrusted stuff, like we raise an exception. So if you consider that an issue, you definitely need to put a try catch around it. You do have the same issue with very large objects. We are loading NumPy arrays. Like if there's an issue with NumPy load, you have those issues here. Some notes, I mentioned that if you have like custom new, it wouldn't work. It does support not just scikit-learn stuff, like we do support XGBoost and LightGBM models because XGBoost and LightGBM, their get state returns a byte array and their set state uses that byte array to load the model. So we just store the byte array. At least XGBoost has a custom format that allows you to load between XGBoost versions. We don't use that here yet. And there's an argument like it would be nice maybe if we do. The roadmap, like we have things like there are more things that we could trust by default, like from NumPy, SciPy, scikit-learn. So there are cases that you save something that is completely legit. If you try to load it, you would have to pass some custom trusted arguments there. We don't do any memory mapping, so if you're doing parallel processing and you load a bunch of files for each one of them, you're loading the file. Whereas with NumPy, you could pass this thing that like it should be kind of memory mapped, which means that if you have multiple processes, like they all like point to the same like data, so like you don't load them multiple times. And we would need to work on a kind of a public protocol that would allow third parties to support like more custom types and have a way for them to register how we should like load and save them. We did not rush to do that because we don't know how to do that in a safe way yet. And we need your help. Please try to break things, report bugs. I'm sure there are vulnerabilities. It would be really nice if people who are not us find them and report them and we try to fix them. And thank you.
Thank you very much, Adrian. There's a question asking you, does SCOPS also help with loading a scikit-learn model trained from version X using version Y? Are there any future plans about it?
No. So what we do is we call get state set state, which is exactly the same thing as pickle does. And the reason you do get a warning when you try to load a model in a new scikit-learn version that is dumped with an old scikit-learn version is that the get state of scikit-learn injects the version of scikit-learn with which it is saved into the dictionary that is saved, and load checks if that version is the same as what it is now, and it gives you a warning. For a lot of models, it should actually raise, because if you load one, it just doesn't work. There are no future plans because so you do have, for example, for XGBoost does that, but XGBoost is pretty much one model. It's a tree. It's doable. You can do that. With all deep neural networks, you can do that. It's a network. You save the architecture. You have the activation functions. Like, it's easy to do that in like across versions. But in scikit-learn, it's an arbitrary Python code. I move my loss. For example, in our gradient boosting, we would move the loss module from this private place to that other private place. And now you load it with a new scikit-learn version. It is trying to load something that doesn't exist anymore. The same goes with like the logic inside the model. So supporting that is in theory doable, but it would require a large team dedicated to just do that, and we don't have the resources.
I don't see any other question here. No, does here anyone have live?
Maybe the last question.
Sure, of course.
Let's assume I have you mentioned the ML model. So let's assume I have loaded an object which points to the different models. Let's say it could be FST, it could be ONX, which are preloaded in the memory. And now I would like to share this part of memory between the processes because I don't want to load the same model multiple times. Is the question. So is it possible to export this model by any address in the memory and then load it in other processes? So for example, loading a model would cost me 2 GB of RAM. If I run 5 processes, it's already 10. So I just want to load it only once in the master process and share it across.
Not 100% sure, but I'm almost certain JobLib has backends that allows you to do that.
Which one?
JobLib. So JobLib is the backend that we use for for parallelization in scikit-learn, and JobLib itself supports different backends. And I know that this is an issue that already existed, and they already have solutions for it there.
But probably for pickable kind of objects.
Things need to be pickleable.
Yes, but that's what I mean. So if the model will just point to the different pointers to memory which are loaded,
then you need to do low-level like shared memory objects like in Python. I personally haven't done it, but I'm pretty sure you can do. And definitely like Scops is not going to be the solution for it, but almost certain you can do that.
Okay, thank you.
Any burning last question? Yeah.
Thanks for the talk. For your conversion service, how do you do that? Is it just a small Docker environment which you throw away after each conversion, or how do you make that safe? Converting from pickle to Scops format?
It is, so that's on the infrastructure of Hugging Face, and it's technically like what in Hugging Face jargon you call a space, and each space is its own Docker. You launch a new one, you do whatever you want to do. It's kind of its own isolated space, so that's fine.
So if there's no other question? Thank you, Adrian, very much. Just wanted to give you a very quick announcement. It's lunchtime now. We did fix the lunchbox issues, so if you want, we'll have vegetarian and vegan options in the lunchboxes as well. Thank you.
What was the lunchbox issue?
They messed up with the orders. They messed up with the order, so we had tuna and ham sandwiches.
Yes, sure.
Good morning. I would have several questions regarding Python in general. Some of them may be new, but can I ask them maybe not now if you don't have time? Or,
No, I mean, shoot.
Okay. In general, okay, because I learned it, I like it, I use it, and poi okay, coding it, ti hanno
Tagliatelle, sì, primo piano.
rimangono abbastanza pulite le sale. Sì, perché fanno, se quando fanno avanti e indietro con le scarpe sporche, poi dopo quando è così, va bene. Sì. Questa porta qui si lascia aperta o la chiudo per l'aria condizionata? Chiudo. Scusa, l'ha fatti chiudere. Il video l'ha fatti chiudere. Qui c'è da fare questo.
sometimes like when people comment or like start commenting, then it comes on. Yesterday I was looking at pictures like I took you one where I captured the whole like the background. It was that nice. We didn't see.
I was still to say. Was the one was standing in front of like the restaurants or something?
Just people didn't care like whether you're taking a picture or not. Just the thing. Like this one. Yeah, like I captured like the whole background.
You have to consider that.
No, I don't know like where you've been to, but like in Belgium, in Germany, Sweden, when you're taking a picture, like they try to go behind you. But this way, someone who see you and like doesn't care for you.
can probably raise a bit the. You know, if we have the control, what do we have to ask? Okay. I'm gonna ask for that here.
all the way. Oh yes, yeah, the small yeah. Workshop. Yeah.
Yeah, yeah, yeah.
I don't have a connector.
You don't have a connector?
No,
Really counting.
yes, yes.
Yeah.
Okay.
ठंडा है
बहुत ठंड लग रही है
कैसे ठीक करना है उसको भी बोल वो एसी का है ना
Has any talk manager
none of
came
them
to you?
will work
No, no. We do have our own though. Is any talk manager came here before?
yeah she has like
Is this your person or?
no the top manager gave this
Talk manager? No, that didn't know wrong. Does it need HDMI? Oh, you get it. Brilliant. Oh, this is one.
Yeah. We're just checking through.
The only thing you have to make sure is that when you connect it, that your display is at 60 Hz.
Okay. I'll have a look. बोल दे
Yeah. Yeah.
Okay.
mic is on
So we're gonna speak alternatively. So like I can sit down when she's speaking. We can use
only
this.
one will speak at a time
Okay, so you use this?
yeah we
This
can
or
use
that? What do you want?
anything is fine. That you can use
Okay. We can use this.
So this?
Okay.
yeah, we can use this also right
Yeah,
yeah
we
it's
can use
fine
this one.
yeah
So today we'll be listening to a session on you've got trust issues, we've got solutions, differential privacy. So for me, the first line of the elevator pitch got me very interested, and I'll read it. What if I tell you I could answer everything about you without knowing you using differential privacy? For me, I would say no, but I'm sure they would prove me wrong. So we have Vikram and Satika going to give us this talk. So a reminder that you go to Slido, you go to the schedule, the Slido link for the questions will be there. Thank you and enjoy this talk.
Hello everyone, I'm Vikram. I'm a graduate student at Columbia University. So we have divided into two parts. The first part would be handled by Sathika and then I'll take over.
Hi everyone, I'm Sathika. I'm a software engineer at Microsoft, and today we are going to discuss about differential privacy and how to leverage Python's PyDB module for it. Let's first quickly go over the agenda. So first we will discuss few concepts of privacy, which are there are three key concepts of privacy. First we will be going over that and their definition. Then we will be seeing what are the risk of handling customer data, and then we will be going on to why don't we simply anonymize data and what are the problems we can face by if we try to just simply anonymize the data. Through this, we will move on to differential privacy, and it's mathematically defining differential privacy and how it works. We will also discuss two key types of differential privacy, and finally, we will move on to actually seeing how PyDB works with the help of code snippets, and we will conclude the presentation with a fun trivia and a Q&A session. Yeah. So privacy is basically the ability of users or a group of users to seclude information about themselves in a way so that they can selectively express themselves. So you can understand it as the ability to control how information about you is processed, stored, or shared. You should not confuse privacy with security. Security is basically who can access your data, while privacy is when and how can they access it. So there are three major concepts of privacy. First is identifiability. It's basically the extent to which a user can be identified with a data set. And then there is linkability. It's basically how, if there are if two or more data records can be used to identify information about a user. So if, for example, there are two databases and a user is present in both the database, we can use maybe their name to link those two databases and get a comprehensive profile of that user. So this is known as linkability. And then there is traceability. So traceability is basically tracing the origin of the data and who accessed it, when it was accessed, and for what purpose. So a very basic example which you might be familiar with is the use of cookies while browsing sites. So cookies can contain sensitive information like name, gender, and age, and the websites that have access to these cookies can easily access your data. So this is a very common example of how your data can be accessed. Now there are a few common attacks that are possible, like privacy attacks that are possible. We will discuss a few of them here. The most common is information leakage. It's basically gaining unauthorized access to your data through security vulnerabilities in the system or the model. And then there is a snapshot attack in which attackers try to take snapshots of the model at certain intervals and then combine them to launch an attack. Then there is a membership inference attack in which attackers try to manipulate models' output to see if a particular customer's data is present or not in that model. And there are other attacks like adversarial attacks, model stealing, and model poisoning. Like for brevity, we won't be discussing them. But yeah. Okay. Now, you all might be thinking, why don't we just simply anonymize the data? Why don't we just remove the information that we don't want to get leaked? So let's see why that won't help with the help of a case study. So there is a hospital that is maintaining record of its patients, and these are the fields that the hospital is maintaining. You all might think that we can just redact name and SSN, which are private to users, and publish the other records. But what if there is another data set, which is a publicly available data set, which is containing the voters list, all the persons who are having the voter right? You will see that there is this zip, birth date, and sex These three fields are common in both the data sets. So using a combination of these, we can easily identify a particular user. This was in fact a true incident in which some politician's data was leaked because the combination of zip, birth date, and sex was unique for him. And yeah, so this is possible. Like linkage attacks are possible in which even though you redact information, but there might be some other data set available publicly through which your like a user can be identified. So why don't we anonymize data? So first is like it might be possible that you are redacting the fields which are actually required for analysis, and it might render the data set useless if you remove them. Second is the linkage attack, which I just explained with the case study. And third is if the data set is large, you can like fire multiple queries, and there might be a sequence of queries through which you can identify a pattern in the data set and identify a user. So these are few caveats of just simply anonymizing the data. Now I would like to hand it over to Vikram.
Thank you. So let's come to the core concept, the core topic of our talk, which is differential privacy. So what's its goal? How is it defined? And what's under the hood? So what basically differential privacy aims is that it's a mechanism by which we address the paradox of learning nothing about any particular individual while still learning multiple things about the population in general. So if you think about any machine learning algorithm, your goal is basically to learn something about the population, like predict, like say, for example, given symptoms, if the patient has a disease or not. So that's our goal. But we still do not need to know if any particular individual in the data has a particular disease or not. So that's the goal of differential privacy. So if you do not abide by certain rules, you might, like if you query the data set again and again, there might exist a sequence of queries in which you can basically pinpoint that a particular user or particular point in a data set has that particular disease. So the goal is to make sure that statistical analysis is possible without compromising privacy. Then when I say query, a query is any function that I can run over the database. So it can be like, what's the average age of all the individuals in the data set? So I'll still be able to answer this question without asking, say, what's the age of Alice? So that's my goal, and that's what a query is. And what I mean by privacy is, so if I have a data set, and if I have a very similar database with me, if I run a query on those two databases and that query gives me a result, so if I look at both of these results, I should not be able to tell that if any particular individual has any particular attribute. So to go into more detail, let's see what's under the hood. So imagine the same situation. I have a data set with like say 100 individuals, and I have an algorithm which tells me, like a machine learning algorithm you can imagine, saying what's the probability of a person having cancer. Now if I have another similar data set in which one particular individual is taken out, so that's what we call as adjacent database, because it's almost the same except for the presence of one individual. I have the same algorithm. I run the queries on both of these data sets, and I have one particular result for each of those. So if any adversary is able to look at both of these outputs and then pinpoint what a particular individual has any attribute. So for example, if Alice has cancer or not, for example. So if that is true, then we say that the algorithm is not differentially private. So it's a property of an algorithm, not the property of the data set. And with the help of differential privacy, we can ensure that both of these outputs are indistinguishable, and so you would not be able to identify any particular user data. So now comes the complicated part of actually defining it mathematically. So so far we have just discussed like what's the goal, but it's very, very well mathematically formulated in this definition. So you would see there are two parameters, epsilon and delta. The epsilon parameter is what we call as the privacy budget, and the delta parameter is what we call as the information leakage probability. So I'll just read out the definition and then I explain it in a bit more detail. So it goes like this: for all pairs of data sets D and D prime that differ in a single participant, so something like this, and an algorithm M. This algorithm can be anything, but we define M to be epsilon delta differentially private if for all S S is the output of my algorithm, so all possible outputs of my algorithm. If the probability that the output for the first algorithm is in S is less than equal to e raised to epsilon of it being in D prime, and with a delta parameter added on top. So what this does is, so to put it simply, like if I have a data set in which it predicts whether a particular individual has cancer, so that's my algorithm. Then I take another data set in which I add a particular user's data, and then so if in the first case the probability of given a symptoms is like say 50%. If I add any particular individual's data, say Ross, and I run the same algorithm, and if suddenly the probability jumps to 80%, I'm almost certainly sure that that particular individual has cancer. So what this does is that the ratio of both of these probabilities should be less than e raised to epsilon. So that's my goal. So I should design my algorithm in such a way that removing any particular individual would not like suddenly spike up the probability so that I know something about an individual. So that's what the epsilon is, but there's another parameter called delta, which is the information leakage probability. In most cases, you would see like delta is also 0. So in that case, we define like epsilon differentially private algorithms, but if like the delta parameter is an additional parameter in which you can almost abide by the epsilon parameter, but we still add up information leakage probability. I've also defined the like official like what epsilon, delta, and m and s would be, but yeah. So now, as Sarthika mentioned, there are two approaches to differential privacy. So we'll go one by one. So local differential privacy is it's basically like how do we store the data. So in the local differential privacy, what we do is each individual data record itself is kind of changed. So you would see like there are 3 records, and we add some noise. We add some noise to all of these records and store it in a central database. So this is the local approach that we are actually tampering or like enhancing the security for each individual record and then storing it. In this case, the data store is itself untrusted because we do not store the original data. And in global differential privacy, what we do is we still store the data as it is, but then while anyone is querying the data, we actually compute the result of the query, but then we add some noise to the result of the query so that we still do not leak anything. In this case, the data set itself or the database itself is trusted, but like we still have untrusted aggregators or untrusted entities which are trying to query the data. So there are some algorithms and mechanisms which differential privacy demands. So algorithm is basically you have a data set, and on the left hand side, the list that we have is all the sorts of algorithms that PyDP supports. So PyDP is a module for exercising differential privacy in Python. So these are the algorithms supported. So bounded mean, bounded sum, bounded standard deviation, and so on. So what these algorithms do is compute the sum, mean, standard deviation, etc. of the data set in a differentially private manner. And then, as I said, in this, we add some noise to either our query result, or either our data. So these are the 3 different kinds of noises we can add: Laplacian, exponential, or Gaussian. We can mathematically prove that adding these types of noises, so I just want to emphasize the fact that these are not like random noises that we add on top of the data. These are very well mathematically formulated, so we can mathematically prove that if we add Laplacian noise or exponential noise or Gaussian noise, we can still abide by this definition that we have here. So these are all the 3 types of noise that we can add using PyDP. Now let's look at the interesting stuff that is actually going to the code and see how a differential private algorithm looks like. So what we are trying to do here is that we have a data set with the salaries of some particular individuals, and we are trying to find the sum and mean of their salaries. Now if you imagine if I do not abide by differential privacy, what I can do is, if I want to find out the salary of Jeff, for example, I do a sum of all the salaries. I do a query of like give me the sum of all the salaries in the database. It gives me a number. Then I remove Jeff from the data set, and then again do the same query. I take the difference, and then I know the salary of Jeff. So this is like very naive, but with differential privacy, what you can do is, with PyDP, I mean, what we can do is we can define. So we'll go one by one. So the first few lines are just importing, and then we imported like the bounded sum and bounded mean of like these two algorithms. Then we load the data set, we pre-process the data set, and this is what we have finally. Then we define epsilon and delta. So these are some random values for now, but we can change it accordingly. Then we do a bounded mean and bounded sum. So what this does is basically it adds Laplacian noise, because that's what we have imported from here. We have imported bounded sum from algorithms.Laplacian. So these few lines set up our differential private algorithm, and then we actually add the noise by using dpSum.QuickResult. So what this does is it gives the sum of all the data set, but it's not the exact sum. It adds Laplacian noise on top of the sum, and then gives you the result. In similar way, we have the dpMean.QuickResult. So basically what QuickResult does is it takes the variable dpSum or dpMean, which is what we have set up in the previous step, and we have added Laplacian noise, and then it actually adds the noise and then gives us the result. And so we no longer have the exact sum and exact mean, we have the noisy sum and noisy mean, and then we just print it out. So yeah. So I again want to emphasize that we have imported Laplacian noise, but we could as well have done like Gaussian or exponential noise in this case. Now we, like for the machine learning enthusiasts or like machine learning practitioners, we also have support for multiple machine learning algorithms in PyDP. So ironically, we have chosen the naive Bayes algorithm as a complex example, but basically I just wanted to also emphasize that we have support for algorithms like these as well. So again, this is an algorithm, and this is a code snippet in which we compute the accuracy of like a data set. We basically use the same API as sklearn, for example. We fit, the classifier itself is called Gaussian naive Bayes, and we import it from the PyDP library. We have a bunch of algorithms here. We have a set of epsilons that we run on, and for each epsilon we calculate the training and test accuracy and like get the results. So this is just an example to show that we have support for machine learning algorithms in PyDP. Now let's look at the things to consider while, so this was all about like how to write differentially private code. So it's still a very active library, PyDP that is. We still have not added support for a lot of things, but there's active development going on. So some of the things to consider is like using differential privacy is not absolutely necessary. So there are some problems in which you would not want to use differential privacy. For example, if there's a bank and it's trying to figure out if a particular transaction is fraudulent, it still needs to know the exact transactions of a particular user. It cannot just look at the aggregate results of users. So when there's individual level analysis required, you cannot use differential privacy, or you should not use differential privacy. If the data is small enough, then still using differential private algorithms won't make sense. It won't be useful as such. Then no epsilon is one size fits all. By that we mean that you actually have to do experiments with a bunch of epsilons to see what works best for your data. Then the next one is not understanding the sensitivity of your data. So sensitivity is defined as like, what if I change some parameter in my data set, and how different the algorithm output is. So by not understanding sensitivity, we might use the wrong epsilon or wrong delta values, which would result in like my algorithm not being useful at all. So it might just output random values by adding noise. Choosing the wrong DP algorithm, again, like it depends on what kind of noise you want to add. We have a bunch of choices. So all of these things basically point to like you need to research your data set enough so as to use the right DP algorithm, the right epsilon values, and the overall like which noise to add, which algorithm to use, and which epsilon to use. Failing to properly evaluate the accuracy of your result. So because we're adding noise, we can expect that the accuracy would not be the actual accuracy of your algorithm, because you're adding noise in the way either you store or the way you query the data. So you need to do a bunch of experiments to figure out the original accuracy of your data. So one more thing which I want to emphasize is when we are adding noise, basically for one query, it would result in like not exact result, it would be a noisy result. But overall, the mathematics points to that if we do a bunch of queries, we do a bunch of results, bunch of queries on our database, data set, all these noises would cancel out, and we would still be able to learn the overall aggregate property of a data set that we want to have. So now, because we do not have a lot of time, I would like go through the trivia questions, and like these are all yes/no questions, true/false questions. I would just like display the result, but yeah, we'll go through each question one by one. So, can differential privacy be applied to machine learning algorithms? The answer is yes. We already saw one example of naive Bayes algorithm. Does differential privacy provide perfect privacy protection? The answer is no, because it's bounded by parameters epsilon delta. So the way you use epsilon and delta values changes on how private your algorithm is. So that's why epsilon is called as the privacy budget of the algorithm. Is it a new concept? So personally, I did not know about differential privacy like during my undergrad, for example. But it was like, it has been around since 2006. There have been a lot of very good books and active research. It's a very active research area and has been since 2006. Does differential privacy guarantee that an individual's data will never be exposed? So again, it's not a very strict guarantee, but you can still limit the risk of exposure. So in an ideal world, every user should be able to define the epsilon value or the privacy budget of that particular individual, but it's like a lot of time away, and we are nowhere close around that. Then does differential privacy require data to be fully anonymized? Obviously, like as we see, we do not need any anonymization. We can still keep all our attributes, but add noise and use like epsilon values accordingly. Can differential privacy be applied to non-numeric data such as text or images? So there are algorithms. So right now, what we saw was like the salary data set, for example. These are all numerical. You might see that we can add Laplacian noise, we can add random numbers. But there is support for data sets such as which contain text or images, and we can add noise accordingly, and our differential private algorithms would still work. Does differential privacy, I believe this is the last one. Does differential privacy allow for exact queries to be made on the data? The answer is no. We still get noisy results and noisy outputs of our queries, and it allows for approximate queries with a control on the amount of error that we can allow. So that was all for our talk. We are happy to take questions. Thank you.
Thank you very much. Okay, so I'll read out the questions that we have. So the first one, can you simply decide you need to add some noise to data, just rerunning the algorithm? Should I read it out again?
Yeah.
Can you simply decide how you need to add some noise to data, just rerunning the algorithm?
Yeah, so basically experimentation, as Vikram mentioned, experimentation is like an essential part of this. So yeah, you have to like experiment and try which fits the best.
I would like to add one thing, like the noise should be mathematically sound, so we should add either like those three types of noises that I already mentioned, Laplacian, Gaussian, or exponential.
Okay, great. The next question. In the global noise approach, is noise added to each record or to a sample of records?
It's for each record, because we do not want any particular. So you can still control how much noise to add, but it's added to each individual record in the data.
Okay, thank you. The next one. Can differential privacy be applied to the exploratory data analysis phase of a project when the aggregation are not clearly defined yet?
Can you repeat it?
Should I read it? Okay, great. Can differential privacy be applied to the exploratory data analysis phase of a project when the aggregation are not clearly defined yet?
Okay. I think you can still not use differential privacy in the exploratory phase, but then once you decide the algorithm you want to use, say what machine learning algorithm you want to use, you can use it in a differentially private manner, which would still protect the privacy of each individual record.
Okay. The next question. Can noise possibly ruin the integrity of the data? How do you decide the parameters and the function of the noise? Is this a trial and error situation?
So basically, as Vikram mentioned, we have to add a particular like mathematical noise. So it won't affect the data because it would eventually the noise would aggregate and give the correct results. So yeah, so that is why choosing the right type of noise is an important part in this. And what was the follow-up?
How do you decide the parameters and the function of the noise? Is this a trial and error situation?
Yeah, it's more like you need to try different values of epsilon, different algorithm, different noises to get to the correct. Like it's not one epsilon fits all. You have to like decide it for your own data.
The next question, would DP replace homophobic encryption, or would you say they are complementary techniques? Homomorphic, sorry. Sorry. Homomorphic encryption.
I am not aware of this, to be honest, sorry.
Okay. What is necessary to research about the data before adding the noise to data? What is necessary to research about the data before adding the noise to data?
Yeah, I would say like the most important thing is like if you try a bunch of queries and you have a particular privacy budget, for example. So if you see that adding a particular noise or using a particular epsilon value like gives very different results, or for say the data is very small, that even adding a small amount of noise actually can lead to like identifying individual records, that would not work. So it's like you need to experiment a lot, and maybe like there are like guidelines on what the epsilon value should be. So in most examples that I see, it's 0.01 or 0.1, which works for most of the average size data sets that we use. But we still need to do experiments to actually like pinpoint to a particular value.
Okay, great. So does anyone else have any other question? Thank you very much.
Thank you.
for coming, and I thank PyCon for giving me this opportunity to share this talk. I thank all the volunteers and all the organizers who made it happen. It's a whole lot of hard work, so thank you all. So a little about me. I am Josiah. I'm an R&D project manager. I design optical thin films for a variety of applications: aerospace, ophthalmic, illumination, a lot of. It sounds complex, but with a name like this, I needed to be in something complex. But good news is, we being in Pythonistas, there is also an easier way. Everybody calls me Joe, so it's simple as it gets. So that's about me. You can find me on LinkedIn. I used to be a musician before getting into R&D. So I also put up some songs once in a while on YouTube, so you can also find me on YouTube putting up some songs. Is there anybody from Bergamo? Italians? Any Italians? Okay, thanks. So there are also songs where I sing in Bergamasque dialect, because an Indian singing in Bergamasque, okay. Because I thought I was mistaken into thinking that was Italian, and I learned that before I learned Italian. So that was the story behind it. And I also have with me Pylock Holmes. If anything goes wrong, it's his fault. So let's get started. Okay, we all know, I'll just run through because I have very, very less time. Digital files can be divided in two, classified into two: text and binary. Though text is a binary format, you would classify, if it is human readable, opening in a text editor, it is text. Otherwise, if you need a special program to open your file and understand it, it's binary. So today we are going to decode, understand what some program writes the binary data, and you're trying to find out how it is written. I don't want to get all of you in trouble by hacking something, so I just also hacking and getting into legal problems. I also want to discuss a little bit of legality behind this. It turns out that the EU allows the decoding and the reverse engineering of files for special uses. Interoperability is one of them. And there are also other uses like educational, to understand. There are also other uses. My necessity was interoperability, because I had multiple spectrophotometers with their own binary data, binary format, and each of their software, the bundled software which they gave, didn't read the binary spectra of the other spectrophotometers, so I needed, there was no interoperability, so I needed a way to get them all working together, and besides, their software was limited for my application, so I designed a software, but I found very little information about how to understand the binary. So it took a little bit of work, but in the end I got there. So before we start decoding a file, we have to understand a little bit of the properties of a data block. There is something called the endianness or the byte order. It could be either little endian or big endian. The little endian is the least significant byte, comes first, and then the most significant byte. Whereas in the big endian is the reverse. The most significant byte is read first. The types of data are also important, because there could be strings, booleans, numbers as in integers or floats, and the size of the data block, because this is dependent on either the type of data or the precision. For example, a float could have a high precision or low precision. So these are the things that we need to keep in mind. This is just a table copied from, we'll be using the struct library from, which is included in the Python. This is just the data copied from that, from the struct page. So today we are going to try to decode a binary format using Python. It is a spectrophotometer data. We will use the struct library, Jupyter Notebook. There'll be a spectra in binary format. This, I'm just giving an example of the kind of data that, that I have. It's a 2D data, as in there are two columns. There is a wavelength column, and there is the corresponding transmittance values for that. In this, it is the visible spectrum. We have only the blue wave. We can see that the blue wavelength transmits about 90%, and the green is almost cut, and red is about 90%. So this is only the visible data, but the spectrophotometer can also contain UV and the IR, infrared. I also have, not only do I have the binary format, I also have the CSV files with the corresponding data. So for me, because I own the software, I use the software to export the CSV files, and then I'll use that to decode the files and then try it on other files. Okay. Now I'll show you the. Okay, this is my folder. This is my folder. I have, as you can see, bottom 5 files are the spectrophotometer data. If I try to open it with my text editor, as you can see, it's all gibberish. So it is binary data. I can't. It's not humanly understandable. I have the corresponding values in CSV files. I'll use 3 files, 3 spectrophotometer data to try to understand if there is a pattern, to identify a pattern, and then I'll use the pattern if I manage to identify it, and use that on the other 2 files to see if it works. So let's get on with the Jupyter. I have already typed everything because for the lack of time. Okay, this is my I just load in the data, and I'm just loading in data of the data which I got from the struct info page. This is the web page of the struct library. There is a lot of information about the endianness, which characters to use, because that the struct library can understand it. So the length of the if you're using a C type, say you're using the int C type, it's 4 bytes length. So those kind of data I'm just loading into, and I'm just loading into my dict for using afterwards in the program. The data frame is just used to display, nothing else. So I have, as I told you, I have everything in this folder. I'm just going to load in, for the sake of simplicity, everything into this variable. I'm just using glob to load a list with all these file addresses, and so it'll be easier for me to access to load in the data. So first I'll take the first 2, which is 0. The index 0 is the sample file CSV sample file. Index 1 is a binary file, corresponding binary file. I'll take 0 and 1 and load it into an integer, which I'm just using as an index. I'll use pandas to load in the CSV file to a data frame. I'll get the number of data points, and so this is it. I've just taken in the CSV, all the data from the CSV into the memory. I'll plot it. This is the spectra, just the plot of the spectra. But while plotting it, I've also loaded the 2 columns into 2 variables for use later. And now I load in the binary data. I'm using the index which I'd saved before, 1. I'm using RB to load in the data as a binary. And I'm also checking the number of bytes in the data. It contains 1324 bytes. I've saved it onto a variable, also that. Okay, now let me take the first 5 values and try to find out if I can locate it in the binary file. I don't know the endianness, so I'll loop between the 2 endianness. This is the little endian, this is the big endian, these are the strings that struct uses. And I've seen that the values were all floats. There are 3 float possibilities, as you can see from here. These 3 are floats. So I'll just loop between those 3. And then I'll scan the whole binary file. The way I do it is something like this. Let's say this is the binary data, and I'm searching for this small binary block. The first iteration at the 0 address, I take 8 bytes and compare it with this, not found. Second iteration, I take the first till I find it. So at this point where I find it is byte 3, not address 3, Pythonic address 3. This will be printed, but I won't stop there. I'll continue till the end of the file. I'll tell you why a little later. I use print statements a lot for this because Python print is green and I love it. No trees were destroyed. So, and it also is easy here. This is not going into production. So I know all you Pythonistas are against print. Yeah. So I ran it. As you can see, it found values with little endian and with F only. The other values it didn't find. So I'm quite sure that it was little endian and F. So now I can scan for the whole file to see if all the values I can find. I hope everyone is with me till now. Okay, because I'm trying to go fast and I'm not sure. Okay, now I'm going to scan everything. Everything, and it found everything. So it found everything. One thing which I note, it starts at 120. The byte address 120, and the last value found was at 1320. This we'll need later. The same thing I'll repeat for the wavelengths. As I told you, it was a 2D data. The wavelengths. I'm just trying for the wavelengths now. I'll run. It didn't find most of the values, but it found the first and the last. Okay. anyway, 10 and 14 were the two values which it found. Okay, we'll try to save it all into a default dict. 10, the highest wavelength was found at 10, byte address 10. The lowest wavelength was found at 14. The value at the highest was found at 1320, and the value at the highest wavelength was found at 120. So I'll just load it into a dict. With one, you don't have a pattern. So let me try with the second, see if some kind of pattern emerges. So again, I'll change the indices. I'm just taking the sample two. I'll repeat the whole thing. I'll plot it. I'll read in the binary. I didn't need to do that. Okay, let's see the wavelengths. Again, 14. Let's not see. And 10. Here 720 was the lowest, and 120 again. This has been repeated. So let me save these. It was 720. Everything else was the same. I'll just load this in. Now we seem to have some sort of pattern. I'm not doing the third one for the lack of time, but I know that the pattern is already there. So let me print out, let me view this. It always starts at 120. This seems to, the values always start at 120, and it seems to go till the end of the file. And the lowest wavelength is always at 14, at byte address 14. Highest wavelength is always at byte address 10. Let us see. This is we don't have any intermediate wavelengths. We don't have the spacing, because the spacing of the wavelengths could be different. It could, in this case, it is 1, but it could be different. So, and the transmittance values always start at 120 and continue till the end. But the number of points can be gotten because we know that the transmittance values are starting from byte 120 and go till the end. We can already calculate the number of bytes. This is how we calculate the number of bytes. The number of data points, sorry. I've calculated the number of data points here. See, so it corresponds with the value that I found in the CSV file. This was what we had input in the beginning. So we have found something which could work. We have found a pattern. Let us see if it can be applied to those other two files which we didn't. We'll load in directly the other two indices which we've not. We'll load in the binary. Let us try to load in the wavelength. It is different from the other wavelengths. The highest wavelength. We load in the lowest wavelength. The number of points is how we calculate it. 120 divided by the total number of bytes by 4. 4 is the number of bytes. For the values in the list, I'll have a loop. I created an empty list and I appended all the values, and I'll use an NP linear space to sort of, I know the number of data points. I I can space out the wavelengths and find all the wavelengths by that. And now we'll compare the two by plotting. I'll also load in the CSV, and we'll compare if it matches. It's a perfect match. It's one on top of the other. For those, if you have any doubts, I'll also, since all the values were reversed, so I just used a reverse. And if I, these are the two values put next to each other. So you can see that we managed to decode a binary file in a short time. Actually, a binary file, I'm just telling this for you, can also contain headers, data blocks, block in identifiers, and junk data. This is just for your information in case you want to. Any of you have the need to use have the need for decoding files, or okay, okay. I thought I was misfit in this PyCon. Okay, I uploaded the Jupyter at GitHub today morning.
This was very insightful. So please keep your questions coming. So there's a question here. In your case, what is the advantage of reading binaries instead of CSVs?
In my case, to export the CSV in the file, in the spectrophotometer software, it was an operation which I had to do it manually for each file. Whereas when I saved the when I ran the scan, it saved it automatically into the binary format. And not only that, the binary format, it made sense always to have the binary format because the binary format also contained many other. In this, we saw only the spectra data, the 2D data. It also had other parameter, the binary data also, there's 120 bytes, also had scanning interval, it also had the parameters, scan speed, it had other parameters which were not, I managed to decode it later, but I didn't present it. It also had other parameters which a CSV file didn't have. So I needed to decode the binary file and then use it.
Okay, great. So does anyone else have any question? Okay, so while we wait for more questions, so I have a question. Can you share with us any challenges that you faced using this method?
Okay, since we have time, I'll show. The first time I got mad because I didn't understand what was happening. You'll see in the code. You can see this abs temp. I'm sorry. Temp. I'm not checking if the value is equal to the wavelength of CSY, but I'm seeing the difference is under. I went mad because I didn't it didn't find. I found out later it is due to one thing called now the name doesn't come, but just to give a, I'll give a small. If I had to. What would you expect the answer to be? Oh, sorry. I'm sorry. is okay. I would expect it to be 0.01, right? Oh, why didn't it? Okay, because I didn't. Because this is something which is, the machines understand binary, and decimal is not, we understand decimal better, but when there is a conversion, it is not exact. There is a little bit of difference between truncation. It's a sort of truncation, but there is another word for it which doesn't come to my mind. So this was what was happening, and I didn't understand. This was in the beginning when I didn't have any information on the web when I started out. So this made me mad.
Okay, great. So
challenges, challenges. Every when you decode anything, it's always a challenge.
Okay. Sorry, I'll get back. There's a question here. Okay, how could you deal with encryption in the binary file?
Encryption?
Yes.
That is a lot of trial and error, because if somebody wants to really encrypt a file, it is hard. It's a lot of trial and error. Usually, till now I've decoded about 6 spectrophotometers and some other files. I've always been able to do with this, but I tried encryption on my own, and it will be very, very hard to decode those kind of files.
Okay, sure. Your hand was up. Okay. Any more questions? Okay. Thank you very much. This was insightful.
Thank you.